CSC 151 compiler construction. And my name is Ghassan Shobaki. All right, so today, like I said, it will be an introductory lecture, and we'll go through the syllabus. So hopefully, by the end of this lecture, it should be clear to you what we will be going to cover in this course, and the work that you are required to do. So this is the compiler course. So what's a compiler? Yeah.
Translate source code into machine object code.
Okay, source code. And what's source code? Yeah.
Languages like Java and C and whatnot.
Yeah. So how do you define these? I mean, how would you describe the difference between these and machine code? Yeah.
The source code is a high-level language, and the machine code is a low-level.
High level and low level. So what do you mean by high level? Yeah.
It combines operators together, such as like adding two numbers together. In the assembly, it could take like 4 or 5 lines for what you want to do, while in high-level languages, it condenses down to 1.
Yeah, this is true. Another way of
high-level language would be something that is meant to be human readable, human understandable, whereas a low-level language is something the computer itself understands.
Yeah, exactly. So this is the key point. The high-level languages that you are used to program in are human readable. So they are languages that humans can understand and that maximize productivity. So that when you program in these languages, you don't have to worry about many machine level details. So you should focus on high level languages allow you to focus on the problem that you are trying to solve by writing this program. So this is the difference, and this is what a compiler does. A compiler translates a program written in a human-like language into machine code. So in fact, this is hidden. So the compiler will take it's going to take something like z equals x plus y, and it will produce something like, what will the machine level code for this look like? So this is an expression, or it's an assignment statement. This is an expression assigned to a variable. So what will the machine level code look like here? Yes?
It would set a register to X. It would add to that register Y, and then it would store that register value back into Z. Okay, this is good. Yeah, so assuming that Z and X and Y are variables, program variables, so assuming that they are in memory. So in your memory, and by the way, in most cases, we assume that the variable names that we work with in this course are local variable names. So they are somewhere on the stack. So you have these X and Y and Z. So these are variables in memory. So what you want to do in order to add these on a typical RISC machine, you will want to load X into some register, load X and put it in some register, say R1, and then you want to load Y, bring it from memory and put it into some register R2, and then do what?
Add R1 and R2.
Add R1 and R2. And
store the result in another register.
Store the result in some other register like R3. And then the final step.
Store R3 back to Z.
exactly. Store R3 back into variable Z. Don't worry about the details. For example, here in today's lecture, we're not going to worry about any details. So X in this case is a variable name, but in actual assembly, it's not going to be a variable name. Assembly doesn't know variable names. This is going to be an address of a variable in memory. So for variable names in actual assembly are going to be addresses in memory, or more precisely, if there are local variables on the stack, these are, this X will be replaced by the offset for that particular variable relative to the starting address for that particular function, which is what we call the activation record pointer, a pointer to the activation record of the function that we are currently compiling. Anyway, we're not going to get into any of these details today, but this is what a compiler does. It takes an expression like this and it translates it into some machine level operations. Is this all what the compiler does? Does it just do the translation?
No. The compiler itself does, but it's only one step in the full process.
Okay, what else does it do?
You have the preprocessor, then the compiler, and then you have the linker that links it to an executable program.
Okay, so what does the linker do?
It links your program or the piece of code with library functions to get it do with the printf or.
Yeah, so the linker does link your program with library functions, but assuming that you're not using any library functions, does this mean that you will not need a linker? Yes.
You still need the linker to link with the C library, which you kind of can't avoid.
Okay, in addition to the C library, so in addition to the library, what does the linker do?
It puts the object code, which doesn't have. It chooses a location to put the object code in memory when the program is loaded.
Okay, but what does linking mean? It's it's going to link something.
It's going to put all you compiled each source file.
Exactly. Yeah. Each source. Now this is the key. Each source file. So your program may consist of multiple source files, and each source file will get translated into one object file. And linking is about linking these object files into an executable. So each object file may not be executable by itself. So linking them will produce the executable in addition to linking with library functions.
I guess in a nutshell, its job is to resolve all external references to the program.
Yes.
Internal and external references.
Yes. But okay. So this is still not. Yeah. So there is still an important thing that a compiler does in addition to doing this. Yeah. Yes, Eric. Yeah.
Would this be optimization as well?
Yeah, exactly. Optimization. Yeah. So it will be applying some optimizations, even though the word optimization is kind of misleading. Using the word optimization is misleading because a compiler doesn't generate optimal code. I'm not aware of any compiler that generates optimal code all the time. Okay. In fact, if someone ever figures out how to build a compiler that generates optimal code all the time, then research in compiler optimizations will stop. But this hasn't happened yet, and it's unlikely to happen. But the compiler generates good code, so it applies certain enhancements. So let's call them enhancements, certain transformations to the code to make the code better, to make it more efficient. Of course, in this course, we will be learning about optimizations, but the focus of the course is not going to be on optimizations. The focus of the course is going to be on how to do the basic translation. So this is the first compiler. This is your first compiler course, and it's going to focus on doing the basic translation from high-level language to machine code, but we will cover some, a fair amount of optimizations, but this will not be the focus of this course. Now, the compiler is not going to do this in one step. So it's not going to go, a typical compiler is not going to go all the way from high level to machine code. In fact, there are some intermediate steps. So there are some intermediate representations of the code. So the compiler will not go, I'm not aware of any compiler that goes from high level to this level of assembly. There is usually some intermediate level. And a very typical intermediate level representation of the code is the abstract syntax tree, which is a tree representation of the code. So let's take an example that is a little bit more interesting. So what if we have something like x equals a plus or a times b plus c times d? Okay, what if this is our input? So in this case, the compiler, the front end of the compiler, is going to parse this, and it's going to translate this into a tree representation that we call the abstract syntax tree, which will look like, for this expression, we have the a and the b, and we multiply them. Then we multiply the c and the d. And then the results of the two multiplications are going to get added. And then you assign the result of this addition to x. So this is the abstract syntax tree. So this is an intermediate representation. It's an intermediate representation of the code. And a typical compiler will generate this intermediate representation, this hierarchical tree-like representation, and it will apply some optimizations to it. So there is the optimizer of the code. Then the optimizer will apply some transformations to improve the quality of the code and eliminate some redundancies, etc. And then it will produce optimized IR, intermediate representation. So this abstract syntax tree is one of the intermediate representations that a compiler may use. So compilers typically use multiple intermediate representations, and the abstract syntax tree is one of them. So it's obviously something that is between high-level representation and the assembly. And then the last part of the compiler, which is the backend, is going to do the code generation. So it's going to do instruction selection. It will select instructions. And there is instruction scheduling, which is scheduling instructions. You don't have to understand, to worry about understanding the details of these concepts, because we'll go through them in detail. So it will find the right ordering of the instructions. Then it will do what we call register allocation, which is deciding which variables will go into registers. And this will generate the assembly. Like in this case, what will the assembly look like? So you have all of these variables. So you're going to load them. For example, load A into register 1, load B into register 2, load, and then add register 1 and register 2 and put the result in register 3. Then you want to do the same thing with C and D. Same thing with C and D, and the result will go into register R5, or you need 4, 5, 6. And then you will add registers R3 and R6, and you put the result into register R7, and then you store R7 back into X. Okay. Now with this structure of the compiler, you have the front end that will take this high-level representation and produce this tree-like representation of the code, the abstract syntax tree. So getting from here to here is going to take us about 60% of this course. So 60% of the time will be spent to understand how the compiler can get from this to this. So the process that the compiler, the process of translating this into this involves what we call scanning and parsing. Then we have semantic analysis. So let's have some high-level descriptions of these. Scanning, so basically you look at your input and you translate this into, you divide it up into tokens or words. In this case, this is one word. Well, this is not a good example because each one is going to be a single word. But if you had a variable like, x, y, 2, 3, so this whole thing is going to be one word, which is a variable name. This is another word, which is an assignment operator. This is a word, this is a word or a token. So scanning is going to break up your input program into tokens or words. And parsing is going to take these words and construct sentences out of them. So scanning is at the word level, taking letters and forming words. And parsing is about forming sentences, which is a complete program. This is a very high-level description. Like I said, we'll spend most of the time in this course understanding these, scanning and parsing processes and how to get from this to this. So this is what we will be spending, all of our time before the midterm trying to understand. Then semantic analysis is about, checking for the if these sentences that we have formed are meaningful or not. So semantics are about meanings. Sometimes you can have a grammatically correct sentence that has no meaning. Like, for example, the apple ate the boy or something. So this is grammatically correct, but it's meaningless. And in computer programs, you can write programs that are syntactically correct, but they are semantically incorrect or meaningless. Like a program, for example, that does not have the right typing. It takes two objects and adds them and assigns the result to an integer, for example. Type mismatch is an example of a semantic error. So it will look grammatically correct, but it's meaningless. So this stuff, this material is going to take us 60% of the time. Then we will look into some optimizations. And we'll spend some time looking into these, instruction selection, instruction scheduling, selecting the instructions, finding the right order for the instructions, and then assigning variables to registers. Because normally, your program will have a lot more registers, a lot more variables than you have registers on the CPU, right? Okay, so this is very much what we are going to do. We will be building a basic compiler. So in this course, you are required to build a basic compiler. And we will be using the C language. You will be building a basic compiler for a basic programming language that has the basic constructs of a programming language. What are the basic constructs of a programming language? So this is an expression, right? So a programming language will have expressions and assignments. What else? Okay, that's within expressions and assignments. What are the basic constructs of a programming language that you can't write a meaningful program without?
Grammar.
What's that?
Grammatical rules.
What kind of rules?
Grammatical rules.
No, the constructs from programmer point of view. So you need to have expressions, the ability to write expressions, to do assignments. What else do you do?
Decision statement.
Yeah, conditionals.
Yeah.
If else, which means the if else that we can't live without. We can't write a meaningful program without. Also, what's the other important construct that we can't write a meaningful program without?
Loops.
Loops. So these are the essential features of a programming language. These are the essential features that we will learn how to build a compiler for. How to build a compiler that takes a program that has only these essential features, expressions, assignments, conditionals, and loops, and translate that into assembly code. So we will not be covering advanced language features like objects and inheritance and all of that, but you will be given the chance to do extra work if you want. So the basic requirement, what you are required to do is to build a compiler that only implements these basic constructs and translates them into assembly language. 90 or 95% of the lectures are going to be on the whiteboard. So we will not be using PowerPoint much. This time I just put the syllabus on the whiteboard, but 95% of the time we'll be doing whiteboard. So we will not be switching, between whiteboard and PowerPoint. So these are the this is what we will be doing in this course. So you have to be interested. From my experience, I only taught it once at Sac State, and if you are not interested, then you will not do well in this course. It's a compiler is a non-trivial piece of software. So a compiler is an intelligent piece of software, and in order to build that intelligent piece of software, there is a lot of science that you have to learn. And this is interesting because I didn't know this, about software until I took a compiler course. So I'm originally an electrical engineer. My degree is in electrical engineering, and I didn't have formal education in computer science, and I was programming. I could program, and I thought of myself as a good programmer, and I thought that I can program anything I want. Until I took a compiler course, I realized that being a good programmer is not sufficient to build a system that is as intelligent as a compiler. So no matter how good your programming skills are, if you don't learn the science that people have developed in order to be able to build a compiler, you will not be able to build a compiler. So you'll have to learn that science. And in fact, that has changed my life, because I was under the impression that computer science doesn't have enough science in it. It shouldn't be called computer science. I thought it's just programming, and I already know how to program, so why should I study computer science? But when I took a compiler course, I realized that there is science in computer science. And I decided, after taking compiler classes, to switch from electrical engineering to computer science. So compilers convinced me that computer science has enough science in it, has enough meat in it, and that's why I decided to do my PhD in computer science. So it's interesting, all of these constructs that people have built in order to be able to have developed in order to be able to build the compiler are interesting, and these are concepts that you have taken in 135. So in CSC 135, which is theory of computation, in theory of computation, you took what were the concepts that you did? Yeah, finite automata.
Grammars.
Okay, grammars.
Yeah.
And
Push down automata.
and regular expressions.
Yeah.
So you need to know these. Now, the good news is that in this course, we will be applying these. So The compiler is an application of these. It applies these concepts to build an intelligent system that we can't live without. The system that everybody uses to write their programs in a high-level language, including Java programmers. So these are the constructs that we will be using. Now, is there anyone who hasn't taken 135? So everyone here has taken 135. So this means that the concepts of 135 will be reviewed fairly quickly in this course. So we will be learning how to use finite automata, regular expressions, and grammars to build a compiler. Okay. And we will not be doing theory here. So if, for example, how many people like the pumping lemma? Okay.
Anyone raise their hand, they can leave.
Okay. Well, in fact, in this course, we will not be doing theory. We will not be doing the pumping lemma. This doesn't mean that theory is irrelevant, by the way. So I just wanted you to know that in this course, we will be applying. This is an application. A compiler is a real system. This doesn't mean that theory is irrelevant. Theory opens new horizons for us. Just keep in mind that all the technology that we are enjoying today, all the electronics and all the wireless systems that we are enjoying today, they are based on the science that people have built centuries ago. They're based on nuclear theory. Electronics is based on nuclear theory, because before people started exploring nuclear theory, they didn't know about the electron, right? And when they started exploring that was the only purpose was pure knowledge. The people were interested in knowing, in understanding the structure of material. So pure theory and pure knowledge may not have applications at some point, but you never know what what applications smart people may come up with later on in the future, maybe decades in the future or centuries in the future. So anything theoretical, anything that is pure theory today, should not be underestimated. It's fine to say I don't like theory, but it's not fine to say theory is useless and irrelevant. This is not true. Theory opens new horizons for us. Theoretical stuff, whatever theoretical work people are working on today, it may have some clever applications sometime in the future. You don't know what clever people in the future, what applications people may come up with for these theoretical concepts. So it's okay to say that you are like most people, don't like to do theory. So most people do not like theory. But it's not okay to say, theory is irrelevant and useless. These are the concepts. So now they should make more sense. We spend there will be an overview first, a couple of weeks. It will be a relatively long introduction so that the big picture. What are the different parts of a compiler and what are the different concepts. So our introduction is going to take 2 weeks, relatively long. Then we'll spend a couple of weeks on scanning, then 3 weeks on parsing, then a couple of weeks on context-sensitive analysis or semantic analysis, then a week on intermediate representations, then a week on basic code generation, how to get from an abstract syntax tree to assembly, generic assembly. Then we'll spend a week on instruction selection, selecting the right instructions, the right machine instructions for a given sequence of code. Then we will do register allocation, deciding how, which variables should be stored in registers. And then a week on instruction scheduling, which is the right order of the instructions. And then a week on code optimizations, the different optimizations. So I hope that these concepts, based on the introduction that I gave today, I hope that they will vaguely make some sense. On a high level, they make some sense. Of course, we will be, as you can see, there will be at least a week for each one of these. So you will understand them better when we get there. But at least I hope that on a high level, what each one of these concepts or components of a compiler, what each one of them is. The first 3 chapters that are that discuss scanning and parsing, we will basically cover the 3 most of the topics in the book. I have the textbook for this is going to be Engineering a Compiler by Cooper and Torczon. So this is going to be the textbook. So the first 3 chapters will get covered almost entirely, but then after we finish the first 3 chapters or the first 4 chapters, we will be covering selected topics. So that's why each one of these topics, they are big topics. Register allocation is a big topic, but we will only spend a week. So we will only cover a subset of what's in the book on register allocation or instruction scheduling. And instruction scheduling is my area of research, by the way. So it's a week is extremely short. It's an extremely short period of time for me. But we will be trying to cover selected topics about these. Questions?